Hey folks, Mr. Dell here. We're going to look at some descriptions, and from those descriptions, create a graph, right? Label our axes and just kind of sketch a graph to represent each scenario. So this is a problem coming from CPM's Integrated Math 2, and this is section 8.2.2, number 8-52. So it says sketch a graph that could represent each scenario below. Be sure to label, we're going to label our axes appropriately, then write a description of the graph. So our graph will be that, we're going to use that, just the graph as we describe it that way. So we're going to just use a graph to describe this scenario. So we've got the height of a baseball thrown from center field to home plate in relation to the distance from center field, right? So if I'm my first graph, I'm going to use my x-axis. I have my x and my y-axis. I'm going to have my x-axis be the distance from center field. Okay. It starts at center field, so it's going to be starting at 0, right? And then it says the height is going to be my y-axis, height. That's the height that the baseball is thrown. So as this is the distance and the height. So as it gets thrown, in fact, actually, maybe, oops, I just lost my axis there. Let me try that again. Maybe I'm going to not start at 0 because the baseball player's got some height, right? So height from ground, it might start here, not at 0, 0. So before it gets thrown, it's being thrown from the center fielder's height, his arm, his head, or wherever he kind of tosses the ball, shoulder height. Then it's going to go up in the air, right? And as it's going up in the air, it's also traveling away from center field. So as it's going up, and then what happens is it reaches its maximum height, and then it starts to come back down, and it ends up going to home plate, and again probably stopping short of the ground because then the catcher will catch the ball. So this would be kind of the trajectory of the ball as it relates to height, right? So we label our axes, and then have kind of a sketch there of what's occurring. All right, B. So then the number of shoppers at the mall each hour during business hours on a given day. So what would that look like? So if I'm going to sketch a graph here for this one, axis a little bit straighter here. So once again, this will be my y-axis, and then this is my x. So the number of shoppers based on time, right? So I might make my time. Time usually falls on your horizontal axis, time of day. So our time could start at 8 a.m. and then end up going to 8 p.m. We'll say in the mall, right? If we had the mall open for 12 hours, and then this would be the number of shoppers. Number of shoppers would be my y-axis, and it could be from 1 to, well, probably more than that. So maybe 5 to 100, depending on the size of the mall. Maybe even more than that. Probably would be more than that. So let me do that. Let me be more realistic here. So let's say we start at 50 shoppers all the way up to 400 shoppers, right? So in the morning, right out the get go, we probably won't have that many. So I might put a point there. And then as the day goes, there would be more and more shoppers. Now the thing is I'm not going to draw a line per se because we're talking about each hour. So it's not what's going on in between, but it's at each hour. So there's 8, 9, 10, 11, 12 o'clock. So this is noon, right? And then 1, 2, 3, 4, 5, 6, 7, then 8 o'clock. So at each, as the day goes, there might be more shoppers coming in, and then in the morning, and then at noon is your maximum, and then maybe they break for lunch, so there's a lot less, but then all of a sudden they get off of work and now there's more coming in again in the evening at each hour, and then they finally at 8 o'clock people start to go home. So something, I mean, it's just kind of a scatter plot of what that could look like, but I'm not going to connect the dots because we're talking about at each hour. That was a key with that one. The last one, C. the temperature of a cup of coffee X minutes after being poured. So um, this one, we know our X because it tells me at X minutes. Our horizontal axis is going to be the time. So X, which is going to be minutes. And specifically what? Uh, time after pouring. So I'll write that. Time after pouring the coffee. And then this is the temperature over here. The y-axis would be the temperature, the temp of coffee, the temperature. So we may say, coffee doesn't stay warm for too long. So I could go by, maybe by fives to 35, 10, 15, 20, 25. Ooh, this would be my 30. Then this would be 35, we'll say. So I think your cup of coffee after 30 minutes is going to get pretty cool. So let's talk through. So in the very beginning, of course, right away, my temperature is going to be the warmest. So it'll be, I don't know what degrees, 160 degrees Fahrenheit or something. It'll be up there, right? So we can have it 160 degrees, and we'll do this in Fahrenheit. So then, and then down here, it'll go all the way down to, we'll say, um, down to 40 here. So 40, 80, 120, then 160. So this is the 160. So and right away it stays warm, but then it'll start cooling off. But it cools off really slowly, and then at some point it just stays cool. Now, if you think about a room, if this is 80 degrees and that's 120, so usually your cup of coffee then will just be at room temperature. So your room might be say at 70 degrees. So it'll just kind of stay at 70 and just continue to be at that temperature until you throw it away or put it in the refrigerator or whatever. But that might be something that looks like there. So that's my interpretation graphically of each of those scenarios.